So next up, we have Gregor from O1 Labs and ZK Security, presenting o1js, the dawn of ZK smart contracts. So thank you, Gregor.
Thanks, Rachel. I hope you all enjoyed your lunch, had some interesting conversations, and are ready for another talk. So my talk is about o1js and ZK smart contracts. My name is Gregor. I work at O1 Labs. I've worked on o1js for about 2 years now. And yeah, I want to start with one of my heroes, Vitalik. So last year at DevCon, Vitalik laid out his vision for the ideal blockchain. What he said was, imagine a world where everyone just runs a node on their smartphone, and when a new block comes in, you just have to check it against a snark, and that's it. You know that the block is correct. So there's one blockchain that actually works like this today. It's Mina. So on Mina, we proved the entire history of transactions down into a single proof with recursion. And so what you get is you can have clients running on your browser, which have full node security. They can verify by themselves that the state that they have is correct. So you no longer need centralized RPC endpoints, or you no longer need to trust them. And that's really cool. But so far there's something missing. So smart contracts, of course. That's why Mina is now launching ZK smart contracts. So not only will normal payments transactions be all merged into a single proof, but now we will have smart contracts running in a proof, and their entire execution will also go into this single blockchain proof that everyone can just cheaply verify. But it doesn't end there, because by moving smart contract execution into ZK, we get additional opportunities to make it more interesting. So these smart contracts aren't like plain old smart contracts. So the main difference with classical smart contracts is that our ZK smart contracts run off-chain. They execute off-chain. And so this picture shows you how this looks like. On the left side, you have an end user machine, and that could be, for instance, your laptop. And you would be, say you are on a website and are interacting with a contract. What happens is that the contract gets called on this website, and it executes there, and it creates a set of updates to the chain, and also a ZK proof that this was done correctly. And this is sent to the Mina network, and on there, this will be verified. So it will actually look up your contract, your address, and it will check the proof against a verification key. So instead of having code that you deploy on chain, you just deploy a verification key. Yeah, so this model has a couple of major benefits. The first one of them is, of course, privacy. You no longer have to send all the inputs to the chain. It all executes locally, so it can have secrets from the user in it, and it's a ZK proof, so it doesn't reveal anything. And this is really a huge step forward, that smart contracts can now have privacy. It enlarges the scope of what smart contracts can do, and will create opportunities for a lot of new kinds of applications. The second one is unmetered computation. You no longer have to count how many instructions these contracts use. So you don't need a gas model because it all happens on the client side. Then you also have a security benefit because a whole class of bugs is eliminated. The bugs that are related to running arbitrary code on a set of on-chain nodes, like re-entrancy bugs, if you know that one. And also, because we no longer need a sandbox smart contracts, they gain a lot of flexibility. So a Mina smart contract could actually make a network request and put the result into a witness, for instance. So it's not as sandbox as classical contracts have to be. So one application of this could be, for instance, oracles. On Ethereum, they post a data feed on chain so that other contracts can use it. On Mina, the oracle could just be on demand. So you just call the oracle contract and it fetches the latest oracle data and gives it to your contract, and it's all one atomic transaction that then gets sent. Okay, so we see that there are a couple of benefits, and I would actually argue that this is all you need. So this model is so much better that you don't really want to go back to on-chain execution. I think probably in 10 years, if you're writing a smart contract, typically it will be that kind of contract. And I also claim that you don't need any on-chain contracts anymore. Okay, so how do we make this happen? On Mina, we will have a hard fork. And it's under the codename Berkeley. And this has been in development ever since I joined and ever since our mainnet launch. And we've been running public testnets since over a year. And now we're ready to go to the next step because we're pretty confident now in our testing. So I'm happy to announce that we'll move to an incentivized testnet. And that will be starting in October. And go check it out. You can see a link there. And yeah, I also want to invite you to participate there. It will be interesting rewards and everything. And I also want to invite you to start building on Mina. And the tool to build on Mina is o1js. So you might never have heard of o1js, and that's because we just renamed it. It used to be called SnarkyJS. So we rebranded it to give it a shinier brand, shinier name, to give it the spotlight it deserves. And also, at this point, I want to mention that SnarkyJS was never the same thing as SnarkJS. It's completely unrelated. So yeah. So what is o1js then? o1js is a ZK framework, and its functionality. So o1js is a ZK framework, and it's written in TypeScript, and you use it from TypeScript. And its functionalities consists of two main parts. First of all, it's a general purpose DSL. So you can define circuits, you can create proofs, verify proofs, everything you would expect from a ZK framework. And you could also use this to do peer-to-peer proving, for instance, or off-chain use cases of ZK. It can be used for that. And second, it's the framework for writing Mina smart contracts. So in addition to having this general ZK DSL interfaces, it also has API specific to writing smart contracts for Mina, like something to get state and interact with state on chain. And apart from that, it comes with a rich circuit library. So it has bit operations, comparisons, stuff that you would expect. Specific to smart contracts, so you have Poseidon, Merkle trees, nullifiers. And very soon, we will also add ECDSA, so foreign field arithmetic, Ketchuk, SHA-2. We will also have a like dynamic lookup feature that you can use to do in one constraint lookup an element of an array dynamically. We have infinite recursion that's exposed at the o1js layer. So in your smart contract, a proof can just be one of the inputs, and you can verify it in your contract with a function call. Yeah, and under the hood, it's using our version of Plonk with some custom gates that are made to make recursive verification really fast. It has no trusted setup because we're using IPA. And also, we're actively developing this. So there's much more to come. Right now, we're developing a KCG backend for some other use cases. Eventually, we will have stuff like folding. And yeah. So sometimes people ask, why are you using JavaScript? Isn't JavaScript bad? So the answer is no. JavaScript is the greatest language in the world. But maybe to understand our motivations, I want to take a step back and look at the wider landscape of ZK frontends. What other people are doing. So I've organized the different frontends here on two dimensions. The first dimension would be, does it write circuits directly, or does it write zkVM instructions? And the second dimension is this a whole new language specific to ZK, or is it using an existing language? And there's different ways you can use an existing language. So this quadrant here, it takes an existing language and compiles it, and then runs it in ZK. So here you, for instance, have the ZK EVMs, RISC-0, and also the latest entry here is o1VM. It's the VM we create for Optimism to run their fraud proofs. And okay, but o1js is in this quadrant here, which you could call the libraries. They don't take the language and compile it, but they just use the language at runtime. So you are building circuits at runtime in this host language. You could call the o1js an embedded DSL. And I really want to say that all of these frameworks are great projects, and they all have a good reason to do what they're doing. And there are very, very real trade-offs between those different choices. You could argue, for instance, that either creating a custom language or going the VM route, both could make it easier to write circuits. But I want to argue that the fact that we are in this bucket is actually very intentional. It has a reason. And I think it gives you some unique benefits that you can't have with the other models. And the best way I can convey this is with a screenshot that I made. So this screenshot I made a couple of days ago. I opened my browser, Firefox, and I went to the developer console, where I opened this on a blank page. And you know that you can just write some code there in the console and just run it, And so what I did is I wrote this code using o1js. It just imports it from a CDN. And then I define a ZK smart contract here. So this has a method, which is really a ZK circuit. And it's just defined in this JavaScript environment, and then I compile this contract to prover and verification keys. I deploy those to Mina right in the same script. I also call the contract. I create a proof, which is a recursive snark, runs in WebAssembly, uses all the 16 cores of my machine, and creates this recursive proof in a couple of seconds right in my browser. Then I'm waiting for this transaction to finish. I'm observing the chain, and I exhibit the final state that's updated on chain. So I have this whole life cycle of a ZK smart contract, just running in this one runtime environment, right? Starting from just defining the contract, and there's no extra steps. It doesn't. You don't need to have a CLI that takes some code in another language, compile it to something, then, I don't know, integrate some awesome file in your browser environment. And I don't know, in some frameworks, there would be a trusted setup here in between somewhere. So it's kind of more seamless, and this really fully integrated, seamless kind of way of calling your, defining and calling your smart contracts is only possible in a JavaScript runtime. It wouldn't work with any of the other approaches. And I think that's really worth something, so that's why we're going this route. Okay, so to summarize that, o1js is the logical outcome of really embracing off-chain execution, because when you move to off-chain execution, smart contracts become client-side applications. So it's perfectly natural to combine them with your entire client-side application. It's natural to have them in the same code base as your UI, to just have your contract be a function that you call from your React app or whatever. So we're really leaning into this. Okay, smart contracts are on a client side, and client side developers will write them and call them. All right. With this, I want to move on to the next topic. I have probably convinced you that ZK contracts are great. But you might reasonably ask, do they cover everything? Like, can we actually build all smart contracts in o1js? Or are there limitations? So my answer is, can we build all of them with o1js? Short answer would be yes. But there are a couple of challenges. So we've been running these testnets for 2 years, and I've observed people dealing with a couple of challenges over those years. So three categories I'm observing again and again are these here. So first of all, you now have to program in a ZK frontend. The next challenge that it's very related to on-chain to off-chain computation is that you have an issue with concurrency. So people who've thought about ZK contracts are probably familiar with that because it comes up very immediately. So the difference with on-chain contracts is that first you send the contract calls as transactions to the chain, and then they are ordered. And then they get executed in order. So at each step, you have a well-defined global state that a contract can modify. And in our model, it's the other way around. We first call the contracts and then send them to the chain, and then they are ordered. So that means contracts execute concurrently. And we really want to have shared state. We cannot get around that because that's what smart contracts are all about. No? So we need to find a way to solve this for ZK contracts. And yeah, the third one is specific to Mina, because we want to have this succinct blockchain. We don't allow a large amount of on-chain state so that it stays really easy to run a node. So that clashes with apps that want to have large state. So briefly summarized, all of these are solvable. So I think programming in a ZK frontend, from my experience, it's for new developers, this is the easiest one. So I know we talk a lot about how hard it is and so on, but in my experience, if you have a zkDSL that's good enough, like o1js, people will figure out how to write their logic in a ZK front-end compliant way. So the other two ones are harder because they're less local. And to solve the concurrency issue, we have a specific protocol feature that I wanted to highlight, and it's called actions. So how does this look like? So actions, they are a way to model an append-only list that lives on each account. And I made a diagram here that shows how this on-chain append-only list can be used to treat concurrent transactions. Okay? So on the right side, you see a zkApp account, which starts off with a state of 0 and an empty array of actions. And then imagine two transactions are coming in concurrently. But they don't modify the state. So they are not conflicting. They just each have an action on them, which says increment. Okay? They both want to increment the state. All right? And then, let's say this is one block, and they get applied, and we just append these actions to the actions field. So we end up with two increment actions here at the end of the block. And then next block comes in, and here we have now another transaction, which represents a second phase, and we call this the reduce transaction. And what it does is it exhibits the actions on the account, and it applies each of them. So it increments the state twice to go from a state of 0 to a state of 2. And then it commits the updated state to the chain. So the point here is that modifying state concurrently is just split into two phases. And only in the second phase, the actual state update is committed to the chain. And note that both of these are just off-chain contract calls. There's no extra on-chain finalization phase that we have to introduce, like other projects do. We can just run this reducing action off-chain, and it's just another contract call. And it doesn't even use any new protocol feature. So the only protocol feature that we had to add was this actions field. And its implementation is not really a list that grows indefinitely, but it's actually just a Merkle list. So we only store a commitment to the latest state of that list on chain. Just this tiny one field element that's on each account that gives us these powerful new ways to solve the concurrency problem. All right. We have many of those instances where we really try to add protocol features to give you the same possibilities in our contracts that you would expect in a classical smart contract framework. And the whole collection of them is what we call the zkApp protocol. So we replace the on-chain code with an on-chain verification key. We still have on-chain state, but it's now pretty small. We have actions. We have composability, so we can call one contract from another contract. We have a way to do tokens. You can get network state and so on. And this protocol is already used to build real applications. So there are a couple of projects building with o1js right now. Something to highlight, for instance, is Lumina, the decentralized private exchange. Yeah, and that's the end of my talk. So I want to wrap up here. And to recap, why you should use o1js. We have this powerful new way of writing smart contracts, which now run off-chain, and we are launching probably the first production-ready ZK smart contract framework. And it really leans into off-chain execution and gives you the unique simplicity and developer experience of just having your entire app in TypeScript. And not only that, but you also get to build on Mina and really be on the state of the art with respect to decentralization, where it's not just a roadmap item, but it's here right now. All right. Thank you, everyone.
Do we have any questions? Are you raising? Is that?
Actually, I have a question about thank you for the talk, about the Mina. I'm not really familiar, so I'm really interested, like, how come it's only 22 kilobytes? Do you have to delete something? If you can, like, really, like, in layman terms, explain, like, what's the magic?
Yeah. So 22 kilobytes is the size of data that you need to verify your balance against so you need a proof and like a Merkle path to your balance to verify that actually that's the true state of the blockchain. So it's what a client with full node security needs. It's not the whole ledger. So the whole ledger is also pretty small because it doesn't store any history. It just stores the current account, but it's not 22 kilobytes. But
okay, but where do you store the whole ledger? On, like, some nodes? Or?
Yeah, the whole ledger is stored on on nodes that run on a server. Yeah.
And I assume that's growing, right? Like the size of it, because it's the ledger, right?
The ledger is like megabytes.
Okay. Thank you.
Yeah.
Hey, so you mentioned that the code is not metered, but the verification, I can imagine it's not constant in time. So is there any security, like safety concerns with regards to that? Like, how do you verify the proof? Like, is it considered safe? Like, do you meter it, or you don't need to meter it? You can just verify it without any concerns?
So there's a fixed size circuit on chain that verifies proofs, and so it has a maximal size of circuits that you can verify on chain. So there's currently it's 2 to the 16 constraints, and the way we want to treat that is deal with that is that if you need a larger computation, there will be a way that you can it's a kind of folding, we call it chunking, that you can have a much larger circuit, in fact, but we will fold it together into a 2 to 16 circuit. Yeah.
So I have a question with respect to the actions and the reduce operation specifically, and I was wondering, if I have a contract and I have a regular stream of actions, so I get multiple actions every block, how will I ever get a stable enough state that I can run a reduce? Because surely I need to know the action list that I'm reducing at that point.
Yeah, great question. So the way we solve this is we actually have versioned the state of actions. So we have 5 different versions on chain which represent the state of actions right now, during application, and at the end of the last block, and at the end of the second to last block. So, and you only have to prove that the action state that you're using is one of those.
So you can essentially reduce an old version of the action.
Yeah, exactly. You would always wait 1 block. It's always a 1 block delay, and then you could talk about that state of actions.
Okay, thank you.
All right, I think that's all the questions we have time for, sorry. But yes, thank you again. Cheers.